Okay, so again, we're going to talk today about the causal past and the causal future. So we're going to consider Minkowski space. I've drawn here the diagram of Minkowski space. So the first definition we need is the definition of a causal curve, which is a curve that is either time-like or null. And then we can define the causal future of P and denote it as J plus of P as the set of all events that can be reached from P by a future directed causal curve. And I've drawn here P, the blue are the null curves, and everything that is contained in the shaded region is the causal future of P. Now, I could replace here past and past and define the causal past, which will be defined using past directed null rays. And it will be all of this. Okay, so that's the definition of the causal future and the definition of the causal past. Why do I need the word causal? No, that's not it. I mean, there is a different notion of future and past you could think about. So what do you think as the future colloquially? No, that's the causal future. So when you think of the future colloquially, you look at your watch and you say, okay, I assign a time label to everything in the world, and everything that according to my watch was later time than a certain time, then it's in the future, right? It doesn't mean that it's actually causally connected. So I mean, you could think about it again by thinking, say, of a Cauchy slice that passes from P. So the Cauchy slice would be a slice that you prescribe initial data and then you can predict the future. So if I introduce a slice like this, which is a space-like slice, this corresponds to a constant time surface for some observer, right? And hence, by virtue of this, I would say everything that is north of it is in the future of everything there, right? So if you were doing numerical relativity, for instance, and you were trying to prescribe data here to solve, say, the wave equation on Minkowski space, then you would be prescribing data here, you would be trying to solve, and you could think of defining everything that is north of there in the future. It wouldn't be the causal future because you wouldn't be able to influence points here from P, right? So to avoid any complication, we're clear about the definition, okay? Yeah, and it is important that there are events that are neither, of course, in the past, in the causal past, nor in the causal future of P. Yep. Yeah. Oh, sorry. Yeah, that should be minus. Yeah. Good. Then I would call it J minus. Well spotted. Okay. So it's important to remember that there are events that are neither in the causal future nor in the causal past, obviously. Okay. So now that we've defined future and past, we can try to define what a black hole is for us. And for this, we're going to draw intuition from the relevant part of the Penrose diagram for Schwarzschild. Okay, so that's the exterior, asymptotics, interior. Obviously, I haven't drawn the white hole and the other exterior because they're not relevant for me. Okay, and yeah, so let's make a couple of observations. I'll write it and explain. So here I defined the future or the past of a single event, but I can think of a set of events, and I can obviously define the past and the future as the union of the past and the futures of every event, right? So if I go and look at scry minus, so past null infinity, all events, all of what I've drawn here is actually in the future of past null infinity, because I can take a null or time-like curve and go from every point on scry plus everywhere on the part of the space-time I've drawn here, right? This is not the same if I start from scry plus, so future null infinity, and look at its past. So if I look at the past of future null infinity, then I can only access what's on the diamond here, right? I can't access what's in there. Conveniently, because this is what I think of as the black hole region. That's what's hiding behind the horizon. So, I mean, I'm drawing intuition for Schwarzschild, but it's not hard to believe, and we will discuss about this later on, that in general, if I think of a black hole with flat asymptotics, then the Penrose diagram will not look much different from what regards the exterior part, right? Because I'll have to have the same asymptotics here, Minkowski space. I'll have to have a horizon that is a null hypersurface, as we'll discuss later on as well, right? So I'm going to be looking at something like this. So this suggests itself, this becomes suggestive of what could be a general definition of a black hole that is not specific to Schwarzschild. So if I have a space-time, which is a manifold and a metric, that has a scry plus, so there must be a future null infinity in my space-time, right? Then I'll say that if J minus of scry plus is not the whole manifold, then the space-time contains a black hole. The black hole will be the complement of the causal past of future null infinity. And I can write it as so the black hole is the manifold minus the past of future null infinity. Okay? If I had drawn the whole diagram, I'd have another null infinity here. So again, you would take both sides and still that would be the black hole, okay? So the black hole is the complement of the past of future null infinity. And right here. The boundary of the past of future null infinity is called the black hole event horizon. Okay, so this is the event horizon, right? And if I take the past of future null infinity, that is its boundary. Okay? Why is that not part of the boundary of the past? Sorry? Yeah. I mean, if I take the past of scry plus, why isn't, say, you know, scry minus part of it, or I plus, or I naught? Why is only the horizon? Exactly. That's not in the manifold. What I've drawn here is not the original manifold. M is the extended manifold after the compactification and the extension, right? So the only part of the original manifold that is a boundary of this region is this. This is a boundary of the past, but it doesn't belong to the manifold, right? It's a boundary of the bounded manifold, okay? Now, I could define in the same way the wide hole and the wide hole event horizon by time reverting, right? By talking, instead of talking about J minus of scry plus, talking about, sorry, J plus of scry minus, thinking about J minus of scry plus, you know, and so on and so forth. I'm not going to write it down because I think it's obvious and it's not that interesting. But you could have exactly the same definitions. Now, a key observation is that these definitions are global, right? That means that I need to know the whole space-time, the whole future, basically, to be able to tell you if there is an event horizon and if there is a black hole. So that is a potential caveat. That is a classic kind of mathematician's definition. It's perfectly rigorous and not particularly useful, right? Because, I mean, you've sacrificed usefulness for rigor here. You've defined it perfectly, but it only applies to spacetimes if you know them in their entirety. So if I give you, say, if you solve Einstein's equations, right, and you don't get an explicit solution in which you can maximally extend easily and so on and so forth and have the whole space-time, but say you solve numerically or do any, you know, and determine a solution up to a point, so you have the interesting, say, part of the space-time, then you can't use this definition, right? Okay, any questions? Well, you don't modify. I mean, if there is no future null infinity here, this definition doesn't apply. I mean, I'm not going to touch upon other asymptotics here, ds and ADS, because we don't have time for that. I mean, for astrophysical purposes, to some level, I think this is sufficient. And we're anyway not going to use that definition much. Okay, so the next topic I want to touch upon is killing horizons. So, as I said, the definition of an event horizon in the global sense is rigorous, but not particularly useful. And a useful notion to kind of understand the properties of horizons, it turns out to be the notion of a killing horizon. So, one thing to notice before I start is that if you think of Schwarzschild, the event horizon is here. This is R equals to M, right? And this is a null hypersurface, as is obvious from the way it's shown in the diagram, right? I can, you know, if I give you a Schwarzschild black hole and you go and find, you know, and you want to find the horizon, obviously, you can tell me, oh, the horizon is sitting at R equals to M in Schwarzschild coordinates, but that's a coordinate dependent statement. So it's particularly hard actually to put your finger on the horizon without, in an invariant way, right? The invariant kind of global definition, to get invariance, you're paying too high a price. You need to know the whole space-time. So is there a way to actually find some local characterization of the horizon? You can't really, at least not in this sense. I'm sure Badri is talking to you about dynamical horizons and other things. I mean, dropped surface and so on and so forth. But in the sense of the event horizon itself, you can. But you can get pretty close to that with a Killing horizon. So, so if I think of Schwarzschild for a moment, then I can actually characterize the horizon in a sort of coordinate invariant way if I think of Killing vectors. So if I think of psi A as the Killing vector that I associate with stationarity, then so I write stationarity here. Then in standard Schwarzschild coordinates, it has this forming coordinate notation, right? So its norm is just C00, which is minus 1 minus 2m over r, and Schwarzschild, right? So for r larger than 2m, the Killing vector in my signature has negative norm. It's time-like outside the horizon. As r goes to 2m, the norm of the Killing vector goes to 0. And indeed, its value on the horizon is precisely 0, and the Killing vector is null. Right? And so for Schwarzschild, it turns out that the event horizon is a null not only it's a null hypersurface, but the Killing vector also becomes null on that hypersurface. So let me now give it the definition of a Killing horizon. So a null hypersurface sigma is a Killing horizon if a Killing vector psi A is null along sigma. It also follows, of course, that psi A is normal to sigma. Okay, so far I haven't related Killing horizons in any way with event horizons, except for the fact that the Schwarzschild event horizon happens to be a Killing horizon. I've just defined what a Killing horizon is with some surface on which a Killing vector is everywhere null, and the surface itself is null, which means also the Killing vector is normal to the surface. Right? So there's a theorem by Carter that says that for static spacetimes, all event horizons are Killing horizons. That doesn't assume general relativity or anything like that, right? And it explains the apparent coincidence. It's not a coincidence that the event horizon in Schwarzschild is a Killing horizon, right? Because that's actually true for any static spacetime. Obviously, Schwarzschild is static. There is a generalization of that theorem by Hawking that says that for stationary spacetimes, that satisfy vacuum Einstein's equations, they're Ricci flat. All event horizons and Killing horizons. Okay. So it also holds for stationary spacetimes that satisfy Einstein's equations. So as we will see in a bit, it will hold for Kerr and in general for black holes of GR because of uniqueness theorems. There are even more general versions of this. So if a spacetime doesn't satisfy Einstein's equations, but it satisfies a version of vacuum Einstein's equations, but it satisfies a version of Einstein's equations. I mean, satisfies G mu nu equals T mu nu, and T mu nu satisfies certain energy conditions, or said differently, the Ricci tensor itself satisfies certain conditions, circularity of Killing vectors or other conditions, right? There are different variants of this theorem and extensions, but it's not generally true. It's not true that all event horizons are Killing horizons, right? What is perhaps more important is that Killing horizons are not event horizons, right? That's not a generic property. So you can't, if I give you a metric, you cannot look for a Killing horizon to find an event horizon unless you suspect that an event horizon is there, and you can't prove that this is an event horizon just because it's a Killing horizon, right? In fact, I mean, the simplest example you could think about is you can take a spacetime with a lot of symmetry, like Minkowski, right? You have a lot of Killing vectors because you have a lot of symmetry, and hence you can take linear combinations of Killing vectors and find, infinite number of surfaces that are Killing horizons, right? It's basically because there are several null directions in Minkowski space that will act as Killing horizons. They're going to be pretty meaningless in many ways, and obviously none of them will be an event horizon, right? So the fact that event horizons are Killing horizons is actually useful to prove theorems, and make statements about the horizon, because it's a property. It gives you a property of horizons of stationary black holes in general relativity. Okay. The definition of and it is useful because the definition of the Killing horizon is local. So this is a local definition. If you give me a space-time, I know that is stationary. I can just take the relevant Killing vector, calculate where it vanishes, check that the locus of points where it vanishes is actually a null surface, right? And hence I can find that this is a Killing horizon just by doing local calculations without necessarily knowing all of the space-time. Okay. Any questions? Okay. So with that, I'll move to the Kerr metric. I'll write down the Kerr metric in Borger-Lindquist coordinates. I'm going to use the usual shorthand notations. So that's the Kerr metric, delta and rho defined as such. So it's obviously a solution of Einstein's equations. So there is some controversy, in fact, about how you derive the Kerr metric by solving the Einstein's equations, and how Kerr derived the Kerr metric. I mean, you know, he maintains that he did it entirely methodically, and there is kind of a rigorous way to do it. A lot of people would disagree with that. I mean, you know, it's not entirely clear how he actually arrives at that metric to some people. I mean, all of this doesn't really matter, of course, because you can take the Kerr metric, calculate the Einstein tensor, verify it zero. So it's clearly a solution to Einstein's equations. Of course, later on, I mean, several techniques appeared with which you can generate the Kerr metric, Ernst potentials and other things. And so there are a lot of very important works on how to derive axisymmetric solutions to Einstein's equations. Okay, so there are two parameters here, M and A. They have dimensions of a length, obviously, the way I've written the metric. Okay. There are two killing vectors, dt and d phi. And of course, the metric is independent of the theta and the phi coordinates. Metric components are independent of the t and phi coordinates, right? So and it's important that neither of the two killing vectors or any linear combination of the killing vectors is hypersurface orthogonal. Okay, so why am I stressing this last point? So, I mean, staticity means that you have a time-like killing vector that is hypersurface orthogonal, right? Stationarity means you have a time-like killing vector that is not necessarily hypersurface orthogonal. So in this case, at least near infinity, dt is time-like, d phi is space-like and has closed orbits, right? So this is associated with axisymmetry. This is associated with stationarity, but this is a stationary space-time, not a static space-time, and no linear combination of the two killing vectors is orthogonal to hypersurfaces. here. So that's why GT phi is not 0. It is a stationary space-time. Okay. So if I take the parameter A to 0, then delta becomes this. Rho squared becomes R squared, right? Delta over rho squared becomes quite familiar. Okay, so if you go to the original metric, you have minus, based on the calculation I did there, just 1 minus 2m over r here, right? In the dr, you get the inverse of that, right? This guy vanishes, this guy vanishes, this becomes, oh, actually, I have a mistake here. Oh no, I don't. This guy vanishes, the square here makes this r to the 4th. There's an r square here. So if you do the calculation, then this becomes Schwarzschild. Okay, so the limit of A equals 0 is quite straightforward, right? And that's the Schwarzschild metric, right? So I'll discuss about this a bit later, but more about this later. But that also gives you a feeling of what is the M parameter. Of course, it will, with an appropriate rescaling of units, will become the mass, right? The M equals 0 limit is slightly more tricky. So for M equals 0, delta and rho take this form. And if you look at the metric, right, with this delta and rho, it's not Minkowski in any obvious way, right? So this doesn't look like Minkowski in the usual coordinates, right? Definitely not Minkowski in spherical coordinates. Which is a bit puzzling if you think that the A equals 0 limit gives you Schwarzschild. So you would think that if you take M equals 0, you're taking away all of the mass, right? You're taking away all of the energy. So what is left? I mean, the puzzle is, of course, solved if you realize that you can make a coordinate transformation, bring it back to Minkowski in usual coordinates. So it is Minkowski. So if you define x, y, and z Cartesian coordinates as such, then just by doing the coordinate transformation, you will end up with Minkowski space in usual Cartesian coordinates. So there is really no puzzle. M equals 0 is Minkowski. Just written. It just tells you that Boyer-Lindquist coordinates do not reduce to spherical coordinates in the M equals 0 limit. It's a different set of coordinates. And it's interesting to understand these coordinates, because it will allow us later on to understand the singularity in the Kerr metric. So, as I said, there is a Killing vector here with closed orbits, phi, that tells you that this is an axisymmetric metric, so there is symmetry around an axis, right? And phi is the corresponding coordinate. So I can just consider phi equals 0, and then the phi equals 0 half plane, and then by rotating that by 2 pi, I could generate the whole space-time. So let's look at that plane. So in this case, what I have is that x is r plus k squared, the 1/2 sine theta, y is 0, and z is r cos theta. Okay, so I can try to draw here this half plane. So r equals 0 means x is this, with y equals 0 and z equals 0. And r equals 0 and theta equals pi halves means that. Okay. So in fact, r equals 0, right, corresponds to a segment here, right? And r equals 0, theta equals pi halves corresponds to a point in that plane. And so this is the point. So r equals 0 in this half plane is that segment, and r equals 0, theta equals pi halves is that point. If I were to rotate the plane to generate the whole space-time, right, then that point obviously would become a circle, and that half segment would become a disk, right? So in the space-time, r equals 0 is actually a disk with radius a, right? And the boundary of that disk is sitting at r equals 0, theta equals pi halves, right? And if I were to draw constant theta and constant r curves, then this would be constant r curves, be like this. I'm not going to draw too many to not crowd the plot. And these would be theta equals constant curves. Okay? So the point is that these Boyer-Lindquist coordinates are not really spherical coordinates, they are spheroidal coordinates, right? And r equals 0, instead of being just a singular point in the coordinate system in the middle, it's actually a disk with an r equals 0, theta equals pi halves is the circumference of that disk. And that will become important to us later, okay? So asymptotically, as r goes to infinity, then the metric takes this form approximately. I'm keeping only the inverse powers of r that I'm interested in here. Okay, so it is asymptotically flat, right? As you see, this is basically the dt phi term written in Cartesian coordinates. And the fall of is 1 over r to the cube times this. So it's fast enough that this guy vanishes earlier than the other things as I go further out. So it actually becomes Schwarzschild before it becomes flat. So it is asymptotically flat. Right, and I get the usual 1 over r fall-offs here. And at the Newtonian limit, you do get the usual GDT is approximately 1 minus the Newtonian potential, where I identify the Newtonian potential as the Newtonian mass over r times the usual constant, and hence m would just relate to the Newtonian mass just in the usual way by using Newton's constant and c. Okay, whereas A is related to a suitable definition of angular momentum. Okay, so you can see it as the angular momentum per unit mass of the black hole. And it's important to note that as A goes to minus A, if you also change phi to minus phi or t minus t, you have an invariance. Okay, so if I go to the metric and I swap A for minus A, but I also swap phi to minus phi, right? Or t to minus t, one of the two, then because of the structure with the squares here, I will get an invariance. I mean, the metric will remain invariant, right? And that obviously has a physical meaning. So this metric describes a rotating black hole. So if it's rotating clockwise and I flip the sign in the way I'm measuring my angle, I start measuring my angle in the other direction, obviously it will look like it's rotating anti-clockwise, right? And similarly, if it's say rotating clockwise and I flip the direction of time, then I'm running backwards in time, it will look as if it's rotated anti-clockwise. So that's exactly the kind of symmetries you expect physically from a rotating object. Okay. Now, let's look at singularities in this metric. So and the inverse metric, of course, metric and inverse metric. And singular at whenever rho is 0, delta is 0, right? So have rho here, delta here. So if either of those becomes 0, then the metric is singular, right? This is obviously a solution to Einstein's equations in vacuum, which means it's a Ricci flat solution. So which also means that the Ricci scalar is 0, right? So I'm going to look at, like in Schwarzschild, I'm going to look for another invariant, and I'll find it in the Kreutzmann scalar. So I want to look at a non-zero invariant to assess whether there are any curvature singularities. So this is the expression of the Kretschmann scalar. And as you can see, there is a rho to the 12 sitting in the denominator. There is an r squared and a rho to the 4 sitting here. So clearly there is a singularity at rho square equals 0. So that's a curvature singularity, and by the theorem I discussed yesterday, that's sufficient to conclude that this is a singular spacetime at rho equals 0, right? So remember that rho squared is r squared plus a squared rho square theta. So because of the plus and all of the squares, rho only vanishes at r equals 0, theta equals pi halves. And that's why I did this so explicitly. So this is the ring, right? This is the edge of that disk. So that's why this is the one on ring singularity in Kerr. So the singularity has the topology of a ring. I mean, the exact shape, obviously, it depends on coordinates, but it has the topology of the ring, which means there's a space-time in the middle that is non-singular. You could pass through the middle, basically. Okay, so so rho equals 0. We understood it. This is a singularity that we can't do much about. It's a real singularity. Let's understand delta equals 0 now. And for this, and of course, delta is r minus 2m r plus a squared. So we're going to take cases. So the first case is when the absolute value of a is much larger than m. So in this case, delta is more manifestly positive, and there is no coordinate singularity. So basically, there is no singularity associated with delta equals 0. I'm calling it a potential coordinate singularity with foresight. And it turns out, right, that as we will not discuss in detail, but you could just you can take the metric, obviously, you can extend it, you can create the Penrose diagram. I'm going to discuss the Penrose diagram in the case of a black hole, but you could draw the Penrose diagram when delta is 0. You can find the maximal extension, draw the Penrose diagram, and this will turn out to be that there is no horizon in this case. That doesn't follow by the fact that there is no coordinate singularity, right? That's a coordinate dependent statement, but you can check that there is no horizon, and hence, in this case, rho equals 0 is a naked singularity, like the negative mass Schwarzschild that you saw yesterday in the tutorial. I stress again, the fact that there is no coordinate singularity doesn't imply the statements under it. You actually need to do the hard work and find it. But if you go and look at the Kerr solution in that limit and find the maximal extension, you'll see that there is no coordinate singularity. Sorry, that there is no event horizon, and hence the singularity at rho square equals 0 is naked. Now, in this case, so for Schwarzschild, we have Birchhoff's theorem, right? That tells you that Schwarzschild is the unique spherically symmetric solution. There is no such theorem for axisymmetric solutions. So Kerr, this is not the unique axisymmetric stationary solution of general relativity. In fact, there are other solutions, right? So you could think of this as being a potentially physically relevant solution, because you can say, okay, it's not a black hole. There is a naked singularity, on that ring near the center. But if I have matter, then obviously I'm solving here vacuum Einstein's equation. So this is not a solution inside the matter. So if I had the star, the star surface was large enough to cover the would-be singular region, then I could find another space-time by solving Einstein's equations with matter, glue everything together and create a nice solution. So maybe that solution is the solution for the exterior of stars, right? It doesn't turn out to be the case. So this, the Kerr solution with this condition doesn't actually provide a decent description for the exterior of stars. And one way to kind of understand this intuitively is that space-times outside rotating stars are far more complicated because the Kerr only depends on two parameters, the mass and the angular momentum, right? Whereas stellar exteriors actually carry some information about the structure of the star, in fact, and would depend on many more free parameters, right? So this generally is not astrophysically interesting. I'm not going to discuss it any further. So case 2. Absolute value of A less than M, then delta equals 0. Yields obviously 2 roots. Right? And strictly R minus is less than R plus, and they're both smaller than 2M or equal. Right? And it can be shown, again, it doesn't directly follow by the coordinate singularity that these are event horizons, right? But it can be shown that R plus, R minus are event horizons. And in particular, we're going to draw later on the Penrose diagram. I mean, you could do obviously that rigorously by maximally extending, introducing the compactification and all that stuff. You can draw the diagram and you can see where R plus and R minus lie, and then you can use the global definition then to determine that they're indeed event horizons. Right, and we'll call R plus the outer horizon and R minus the inner horizon because of this inequality here. Okay. So case 3. The marginal case, absolute value of A is equal to M, right? Then R equals M is a double root. Right? And this is what we call an extremal black hole. So intuitively, what is happening is that if you start from case 2 and you think of cranking up A higher and higher, what you see from these formulas is that, so if you were to start first through this case and start cranking A down, right, going towards Schwarzschild, then what you would see is that R minus is shrinking, R plus is getting larger until R plus reaches 2M and R minus reaches 0. Okay, so that's kind of the smooth limit of Kerr to Schwarzschild as you kind of spin it down. If you were thinking of spinning it up, you start cranking up A, then what you see is that R plus now is shrinking and R minus is growing till they meet each other at R equals to M, and then you get the extremal black hole. Okay, so this is basically the black hole with a maximal angular momentum for a given mass. I'm not going to, we have very limited time, so I'm not going to discuss it much. I'm just going to tell you that it is really a different beast than Kerr. It's believed to be unstable. I mean, extremal black holes, similarly with maximally charged electrically charged Horizon Nordstrom black holes, and it has qualitative differences with Kerr, right? So I'm not going to discuss it any further. So for the rest, I'm just going to focus on case 2, which is basically the Kerr black hole. Okay. Now, before I draw the diagram, I'm going to talk about the Kerr black hole uniqueness briefly. So this is a series of theorems, primarily but by Carter, Robinson, and Hawking, with work by many others as well, trying to establish the uniqueness of Kerr as a black hole metric. So I'm going to kind of semi-colloquially state here the theorem that that comes by the combination, every stationary asymptotically flat black hole solution to Einstein's equations in vacuum is Kerr either is a Kerr black hole, potentially extremal. Okay? Absolute value of alpha larger or equal to m. Okay, again, let me stress, this is not a version of Birchhoff's theorem in axisymmetry. I'm not saying that any solution is Kerr, that is in fact, there is no reference to axisymmetry here, right? The assumption is that the solution is stationary, asymptotically flat, and it is a black hole, then it's Kerr, right? So the logic is you get axisymmetry for free, and then there are no other black holes. There are no black holes that solve Einstein's equations, basically, that are non-Kerr. There is a bunch of huge family of axisymmetric solutions that stationary axisymmetric solutions that are known. You can write them down explicitly. They're not Kerr, and the way that you kind of circumvent this problem is that they're not black holes. They have singularities in or outside the would-be horizons. Okay. So interesting kind of corollaries here is that small perturbations to Kerr in the case of the non-extremal die off exponentially. Right? And the characteristic time, I'm not going to talk about surface gravity, but I mean, for those of you that know, obviously the characteristic time depends on the surface gravity. And so this is what people refer to more technically as mode stability, right? Then which is not the same as linear stability or non-linear stability, right? And of course, I'm not going to write this down, but the observations we have so far suggest that Kerr is consistent with the observations, and of course, can always do better in this respect. Okay. Any questions? Yeah. So this is mode stability. You take Kerr, you linearize, then you expand in spheroidal harmonics, basically, and then you show that there is decay there. That's not the same as full linear stability, and it is not the same, obviously, as non-linear stability. So I mean, this is both. There are already results. I think we're very close to people showing that Kerr is non-linearly stable. Non-linear stability basically has to do with, I start with generic initial data and eventually I form Kerr, basically, right? So I think people are very close to proving Kerr nonlinear stability. There are results for Schwarzschild, there are results for slowly rotating Kerr, and so on and so forth. So there's a program basically going over years to get to this goal. You mean that the tails? Yeah, there are tails, but I mean, this is also the, I don't want to go into these complications. I mean, the tails relates to the fact that, I mean, QNMs are not a complete basis and so on and so forth. I mean, so it's not clear if there's another basis or, you know, where the tails will not be there. But I mean, let's not get into these details here. They're not going to interest us. Any other question? Okay, I think I've run out of time already, have I? Oh no, I have another 20 minutes. Sorry, I got confused about what time we're starting. Okay, then that's perfect. Okay, so I'll go here probably and talk about the Penrose diagram. Okay, so the Penrose or conformal diagram for Kerr is obviously not that easy to derive rigorously. So in principle, you start with Kerr. You can introduce kind of Kruskal-like coordinates for Kerr to maximally extend it. Then you can compactify and introduce the new manifold and end up rigorously drawing the Penrose diagram, right? So obviously this is what people have done. I'm not going to do that in the blackboard. It's not feasible really, but we can, same as I did yesterday with a collapsing star, because of the level of abstraction of the Penrose diagram, in fact, you can draw it by intuition to a certain level, right? So I'm going to start here. That's right. With the Penrose diagram of Schwarzschild. So that would be the Schwarzschild extension, right? And I'm going to rely on your intuition to say, look, I mean, at least in the asymptotic region that we live in, the asymptotic structure will be exactly the same in Kerr, right? And there's going to be an event horizon, which in this case is the outer horizon that is sitting at R plus, right? It turns out that this is a null surface, and now you kind of expect why it's a null surface, because it's of course a killing horizon, right? So it's going to be like that. Obviously, the interior of Schwarzschild, also there is here time reversal, and there's going to be another asymptotic region, again, by the same symmetry of Schwarzschild. I do get to Schwarzschild at the appropriate limit after all. So I think it's not hard to believe that that part, these two parts of the Schwarzschild diagram will still be there, right? The exterior will be qualitatively the same in the Penrose diagram, and nothing will change. The real question is, how do I draw the rest of the diagram? What happens in here and in there? And as I said, there is time symmetry, so I only care about the time reversal, basically symmetry. So I only care about this. That should just follow by time reversal, right? By virtue of the fact this is a stationary spacetime. Okay, so now what happens in here? Well, I have a second horizon. This is the inner horizon, right? And this is also killing horizon. So this is also has to be a null surface, right? And it turns out that this is here. And again, that makes sense, because if you think of somebody trying to fall in, they have to cross the outer horizon, then the inner horizon, right? There needs to be a pair because of the right-left symmetry, right? And they would have to cross the inner horizon and basically one of the, the outer horizon, then one of the inner horizons before they encounter the singularity, if they're heading there, right? So this picture makes kind of intuitive sense. And I'm repeating it down there. Then I have to think about where I'm going to draw the r equals 0 surface, right? Which, remember, r equals 0 now corresponds to that disk, right? And only the edge of that disk is a singularity. And in fact, r equal constant surfaces in the exterior would look like this, right? In here, once I've crossed the horizon, we start looking like that. And then up here would start looking like this again. And you can go and calculate that indeed r equals 0 is a time-like surface, and it lies here. And by symmetry here, and here, and there. Okay. Now, you can ask yourself, okay, I'm trying to draw the maximal extension. So whenever I don't reach an infinity, or I don't hit the singularity, then I should be able to have more space-time, right? So I should be able then, so if I start from here and I go towards singularity, right? If I hit the ring, then I've hit the singularity and I cannot extend. But actually I can pass inside the ring. So if I pass inside the ring, there must be more space-time there, right? And it turns out that, so if I pass inside the ring, then I'm accessing this region or this region or that region or that region. And here, what I get is another asymptotic region, right? So there's another I naught here, right? Scry minus, scry plus, scry plus, scry minus, I naught, right? And that part now is basically, so this part, the space-time here is really, the singularity sitting at r equals 0 is naked for what regards that asymptotic region. And you can kind of intuitively understand why this is a naked singularity. So if you go to the Kerr space-time, this is really the extension beyond r equals 0. So it's really, in the original coordinates, that would be negative r's. I would be extending in negative r's. And if you try to go to the original space-time and flip r to minus r, this is no different than flipping m to minus m. Not everywhere, but in the relevant terms. And you will see that you get a structure which is very similar to the negative mass Schwarzschild that you saw yesterday, right? So again, I'm relying on your intuition here, and I'm explaining you why these things make sense. Obviously, you need to calculate them to convince yourself entirely, but obviously people have done that. So by symmetry, you'd get the same structure this way, right? And then you ask yourself, okay, but what happens if I don't go? So if you cross, obviously these come and touch here, and the same is for the rest of the diagram. So you say, okay, if I start from here, my universe is here, I fall in, right? I fall in, I cross r equals 0, I end up here, I can end up in scry plus here. So I ended up in that point. That seems feasible. Then I run out of space-time because I hit an infinity, right? That's fine. But what if I don't hit the singularity? What if I go here? There must be more space-time there, right? And indeed, what happens there is that you start, what you're getting is, you're getting a copy of what you have. So you can take this bit of the space-time and go and glue it up there, and glue it up onto itself, and similarly to the bottom perpetually. And that forms the maximal extension of Kerr. You can glue it onto itself, basically, to perpetuity. So I'll try to draw here, kind of just a larger version of it. Yeah, this is the Kerr black hole, right? So the naked, so the case one would just look like the Schwarzschild naked singularity diagram, right? And the extremal is also different.
These two, the ring would collapse like that.
Yeah.
Of this,
yeah, the extremal has collapsed and has a different diagram, but I'm not going to draw it. So if you take, say, an asymptotic region here as being your universe, so let's assume that this one, so what you have here is this is your universe. So this is a black hole, this is a white hole, right? But then this is a white hole again, and this is a black hole again for another region, right? And this continues to perpetuity. So there's a ring singularity here, there is a ring singularity there, right? I'm not drawing them as curly lines because remember in the Schwarzschild Penrose diagram, every point is a sphere because I've suppressed theta and phi, but of course that's an isometry because I have spherical symmetry, right? Whereas here that's not the case. I've suppressed theta and phi, right? But obviously only I have an isometry along phi, but not along theta. So every point, so here there are singular points, the ones that are sitting at the edge of the ring, but there are also the points that are inside the ring that are non-singular. That's why I haven't drawn the whole thing as curly, right? Only R, so this is R equals 0. R equals 0, theta equals 2 pi is the singular points, right? The rest of the points that still belong to this line are non-singular, which is how I can cross, right? That's why I'm not drawing this curly. So if you start, say, from an event here, and you're a time-like observer, you could do something like this and end up in this asymptotic region and say, end up on this I plus there, right? You could end up here, which is what would happen to you if you never fall into the black hole. You end up in the I plus of your own asymptotic region, right? You could also do this and travel forever by crossing to black hole, white hole, black hole, white hole, okay? So this is the peculiar structure of Kerr. Let me concentrate on what happens to this guy that comes like this and comes into this region there, okay? So this is going to bring me to the topic of closed time-like curves. So consider a curve along which in Boyer-Lindquist coordinates you have constant t. Theta is pi halves, so that's an equatorial, that lies on the equatorial plane, right? And then assume that r is minus 2m times epsilon, where epsilon is constant and it's much smaller than 1, but positive, right? And assume that epsilon squared is much smaller than a squared over 4m squared. So I'm selecting a very specific curve. As I told you, this lies in the negative r's domain, which is actually sitting in that triangle, if I think in terms of the original coordinates. It's a t equals constant curve and a theta equals pi halves curve, right? So that, and then I can go to the metric and I can look at the line element and I can do a small expansion, an expansion in epsilon, which I'm assuming it's a small coordinate. It's a small number, right? And I will get that this is what I'm left with from the line element. So T is constant, theta is constant, R is constant. So all it's changing is phi in this. That's why I only have d phi here, right? And what you get here is that for a very small epsilon, right, then this ds squared is negative. So this is a time-like trajectory. So I'm moving along phi, right? And for small enough r's, so I'm close enough in a sense to r equals 0, right? But on that side, then I have a time-like trajectory along phi. So I'm moving in the phi direction, but I'm on a time-like curve. And of course, phi has closed trajectories. If I move all along phi, I'll just meet myself again. So this is an example of a closed time-like curve, which is a causal conundrum that happens in that part of Kerr. So if I were to manage to cross through the ring singularity and go to the other side, I would be in a part of the space-time where my notion of causality collapses. I can just move along closed curves and meet my younger self. Okay. So sorry, say it again. Yeah, and constant. So I'm assuming that this just defines a curve. I'm saying I'm on a curve where t is constant, theta is constant, r is constant, right? I'm just selecting where in the space-time the curve is by choosing r, and hence I'm moving along the phi direction. If I don't fix the 3 coordinates, then that's not a curve, right? I mean, it's a plane. So there are two disturbing, I mean, depending on your perspective, there are multiple disturbing things about the causal diagram of Kerr, right? One is obviously these closed time-like curves. I mean, nobody should be happy that there is a part of the space-time where this thing happens, right? Another weird thing is that there can be observers that start from here and end up in other asymptotic regions and continue to live happily, right? Or move perpetually into the future, right? This also doesn't somehow sound good. The expectation is, of course, that most of this diagram is just purely irrelevant. So in the same sense that the white hole part of Kerr of Schwarzschild is irrelevant because it doesn't form from collapse, you can easily say, if I live in this asymptotic region, I should actually dismiss all of the bottom part of the diagram. I don't really care about this. This is my region, and maybe the black hole is real, but the white hole and everything below it I shouldn't care about, right? But you still have to deal with what's on the north of your asymptotic region, right? So I'll say two things about this. First, I'm going to talk very colloquially a bit about cosmic censorship. So cosmic censorship started, of course, as a conjecture by Penrose, which people colloquially understand as black holes should be covered by horizons, right? Singularities should be covered by horizons. But of course, mathematical relativists have formulated cosmic censorship in a way that makes a lot more sense mathematically. And there are two versions of it, the weak and the strong cosmic censorship conjecture in mathematical parlance. And these both relate with a maximal Cauchy development of initial data. So it becomes about predictivity, really, rather than discussing about whether singularities are covered and so forth. And the logic is that I should be able to set initial data on a Cauchy slice and use this data to predict the future, basically, in that space-time, how fields or the space-time itself behave, right? I mean, I'm not going to delve into the fine details between weak and strong, but mathematicians don't only worry about what happens to observers in a sense, because that relates to predictivity. So a picture like in Schwarzschild, a picture like this, where you have an observer and they either go here nicely to I plus, which means they live forever basically, or they go and hit the singularity and get destroyed by the singularity, makes mathematicians happy. They like observers to be destroyed. And the reason is that an observer that goes in, they can predict, if I set up initial data here, I can predict what happens to the observer after when they hit the singularity, but I don't care because they're destroyed, right? If the problem here is that I can choose a space-like surface here, give some data, and then predict what happens in part of the space-time, say. But then the observer can escape from that part of the space-time and still not get destroyed. And that is what would annoy a mathematical relativist, right? That basically you think that we can't predict what is happening after that, right? At what seems to be a reasonable part of the space-time, right? So to a certain level, you can link cosmic censorship with whether the rest of this diagram actually exists or not, right? And this is kind of the more modern thinking. I mean, this relates to, so if I go here and draw only that part of the diagram, right? So if this is my scribe plus, I naught, right? This is my horizon, R plus, and this is R equals R minus, right? The inner horizon. There is something disturbing already there, which Penrose noticed in a brilliant paper. So if this is, take two observers, they both start from this point. One goes straight to I plus, the other one crosses the horizon and eventually reaches the inner horizon to R minus, okay? Now, think of this guy here as having a laser pointer, and every second of his clock presses the button and sends photons to the other guy. So these are null trajectories, so they will go like this. So the observer that has fallen in is receiving and continues to receive photons from the guy outside, right? All the way to the point that he reaches the inner horizon. Only there will they kind of lose contact, right? And that's a very disturbing picture because it takes infinite time for the external observer to reach I plus, right? And the other guy reaches the horizon at finite time. So of course, the amount of energy that he would have received in photons from the guy outside, from the observer outside, will be infinite, right? So this suggests that there has to be some sort of instability associated. The only kind of way to avoid that is that there has to be some sort of instability associated with the inner horizon, right? And the region of space-time related to the inner horizon. And people, that observation by Penrose, of course, triggered work in this. This is known as mass inflation instability. People have looked into this. I mean, and there's also much more recent work in this, at a non-linear level. And in reality, I don't think anybody believes that that part of the space-time really exists as a maximal extension, right? Something is happening along the inner horizon, and there is some sort of reason why space-time has to end there, right? So I don't want you to take the Kerr interior. So the Kerr interior is kind of an active, understanding the Kerr interior is an active kind of field of investigation, right? It's clearly not relevant through the exterior, because anyway, it's covered by the outer event horizon, right? But it's very interesting kind of, in the context of understanding general relativity and kind of mathematical physics in general, right? But you shouldn't take it seriously as this is the interior of Kerr, what we're drawing in this diagram, okay? So I'll stop here, and tomorrow we're going to start talking about black holes beyond general relativity and how that picture could change if you deviate from GR or the standard model. Okay. Thanks.